Hello, this is the video for multi-compartment kinetics. Multi-compartment kinetics is a complex concept. When I was a student, pharmacy student, I never understood this multi-compartment multi-compartment kinetics, because we did not have, our teacher did not have those animation. We didn't have that good textbooks with so much of illustration. But this is a simple concept in kinetics. If you have some imagination and if you understand the overall distribution of the drug in the body, that is easy. So first, let's do some thought experiment. Let's think about our body. What all we have learned before, it is single compartment model. That means forget about we administer drug in human body. We have to consider, think about, you have here we have a tank here. We have a tank here. Oh, what's going on? Let's pause the video. Sorry for the interruption. Let's do some thought experiment. Let's for the timing we forget about the drug is administered to human body. Let's think about, we have a tank here. We have a tank here, and this is full of water. Let's assume this is full of water, and this is an outlet, and this is where drug elimination is happening. And now this is a water tank. We are not administering drug to human body. We have water inside. This is all water. Now we are administering a dye, or think of this is our drug. So we are administering drug. So what is happening? This dye will mix with the entire water. And then some of those dye, we have this extraction here, some of the drug is coming out, the dye is coming out, cleaning the water. So we have this dye cleaning the water. So this is a compartment, and this is called one compartmental model. In our case, if you think about this dye, it is the concentration of the dye in the tank is decreasing in an exponential fashion. It is called mono exponential fashion, because we have mixed the dye with the water, and we have that extractor here which is getting rid of the dye from that container, and that how the concentration is decreasing. It is mono exponential with time and concentration. This was the assumption for all the classes we have had. So this is a single compartment. So although we have been talking about all those good stuff about the human body, in fact the assumption is we administer drug in a compartment, and it has an elimination, and we are administering the drug. and the concentration is falling in an exponential fashion. It's called mono-exponential because it is the same. There is no change in the exponential fashion. But in case of multi-compartmental model, in case of two compartment model, we have a tank here, and that is also, it has an elimination, but it is connected to another tank which is bigger than this tank, but it drag does not eliminate from here. So you think about, again, let's go back to the concept of the water, and here is our drag is coming, and drag is eliminating from that elimination from this route, from this compartment. But under the assumption of two compartmental model, our drag is also with time, it is distributing here, which is a bigger compartment. So what is happening here? So drag eliminates always from this compartment, which we call central compartment, or you can say plasma compartment. So, and as you can see, as drag is eliminating from here and also distributing to another compartment, as a result, what is happening to the concentration of the drag? So first there will be, think about, this is central compartment, these are our tissue compartment, and then because of the distribution of the drag from central, from our plasma to tissue compartment, there will be a sharp fall in the concentration of the drag. So you can see there will be a sharp fall in the concentration, because some drag is eliminating and also it is distributing into the another compartment. And then at certain point, all the drag here, there will be an equilibrium. Because of this equilibrium, after certain time, that here so there will be two phase. It is sharp fall because this drag is moving from this compartment to that compartment, from central or to peripheral compartment. Also, it is called central compartment, and this would be called peripheral. You can, for simplicity, you can say plasma, and this one you can say tissue. This is tissue compartment. So again, to understand this concept, if you remember, we have been talking about, for one compartment model, there is sharp in one phase, drag concentration decreases from the same compartment via elimination. But here drag concentration decreases, it follows a Biexponential fashion. See here, the better curve is this. There will be always sharp fall, and then will be elimination. This will be called distribution phase. And this is elimination. So this concentration is decreasing because of movement of drag from this compartment. So again, if you understand this concept, I'm spending a lot of time in this so that I can make you understand this compartmental model, which I never understood as a student. So let's go back to the compartmental concept. One compartment model, we have one tank, and there is elimination. So here we have water. This is water tank, and we are administering some drug. So drug instantly distribute all over the tank and starts eliminating. As a result, our profile would be like this. It's called mono-exponential fall. Mono-exponential fall. As all you have seen that absorption, elimination, it falls that way. So now we have a drug which moves from this compartment to another compartment, and there is no elimination from this compartment. Always elimination is from there. So here we have another bigger compartment, and drug moves from this compartment to that compartment, and it comes to an equilibrium. So for this reason, we will have biexponential fall. First concentration falls and then it goes like that. So this would be the distribution, and this is elimination. Okay, this is elimination. So as you can see in our equation, it was C is equal to C0 e to the negative kt. So we have as two exponential term here. You can see two exponential term. That means here you can say C0 e to the negative alpha t, C0 e to the negative beta t. So the total concentrations, our C would be, if you see the initial concentration, A e to the negative alpha t plus B e to the negative beta t. So it is just two exponential term we have combined together. And now let's go back to our note. So here I have tried to explain again what happened in case of distribution. We administer the drug in the central compartment. During this central compartment, there will be some elimination. With time, drug will distribute from central to peripheral compartment. And at some point here, there will be an equilibrium, central and peripheral compartment, but elimination will always be central compartment. And here the sharp fall again, it is drug is eliminating from the central compartment. Always you remember, when it is an equilibrium, is a dynamic equilibrium. When drug is decreasing from the central compartment, drug will come from the tissue compartment to the central compartment to maintain the equilibrium. This is all about two compartmental model. So when you are studying about compartmental model, you just completely forget about human body. You just think about we are dealing with two compartments like this one, central compartment which is plasma, peripheral compartment which is tissue compartment. So this is what you have to remember here, and I have some animation which I will show during the class. As here is also one compartment model. Now things are easy. You see, this is mono-exponential. This is the equation, and we know that. So, and drug eliminates from the one compartment. But in case of central, and there is a difference between central and peripheral compartment. The central compartment, the drug instantaneously distribute in the body, like what I have shown in that picture, that dye instantly mix with the water. So there is a mono-exponential fall of the concentration of the dye. And then also you have to remember this two here. If you see two phases, distribution and then elimination, this is also first order, and this is first order too. First order. So that's why two phases. So to make things better here. So this is also first order. So that's why it is written that first order process controlled by drag amount in the central compartment and redistribution from the central to peripheral, also a first order process. Amount of drag, this is controlled by the amount of drag in the peripheral compartment. Here I have explained again. As you can see, this is one compartment model. Drag instantaneously distribute throughout the body. But in case of two compartment model, drag first goes to the plasma and then it goes to the tissue compartment. For this reason, we will have a pattern like this, distribution, and this is elimination phase, distribution and elimination. As you can see, the concentration, what is going to be the concentration of the drag? In plasma is going to continue to fall. In tissue, there will be an increase and then fall. So they are going to fall at certain, after distribution, their concentration, elimination, or concentration in the tissue and central compartment is going to decrease at the same rate, at the same time. So this R is again same thing. Here, central compartment, peripheral compartment. You can say plasma, tissue, distribution and redistribution. Always elimination from the central compartment. This concept of elimination is from the central compartment. As you can see, tissue compartment, tissue of plasma drag concentration goes up with time, and plasma, it decreases like this here. So this is the tissue compartment's concentration, and plasma is like this. Always you have to remember two compartment. If you think about two compartment, one of this and another is bigger compartment, which is tissue compartment, plasma concentration always go down like that because it is plasma like this, but tissue compartment initially is going to be increase a little bit and then will go down. Here the equation, as I have mentioned, this is the two equation are explained like this. This is first exponential term, this is the second exponential term. It is nothing but, you can see, it is, we in our equation we have used C is equal to C0 e to the negative kt. No? So this k is alpha here, which is called distribution rate constant, and then here another k we have, it is called elimination rate constant. This is elimination rate constant. AUC and clearance, as you can see, we have two compartment. We have two compartment, 1, 2. So so we have to consider the AUC both in central and peripheral compartment. For this reason, AUC would be this, the concentration in the peripheral central compartment, concentration in the peripheral compartment, and divided by rate constant. If you remember that, this is the AUC of the distribution phase, AUC of the elimination phase. As you can imagine, if we use one of these, for example this one, there will be an error. It's erroneous distribution of volume distribution. We'll explain to you later. Here the same thing over and over so that you understand. This is the elimination rate constant. Here we have distribution rate constant. And volume in the central compartment. Always you have to remember the volume of the central compartment is smaller than the volume of the peripheral compartment. So I will expand more on on purpose. I always try to make smaller central compartment. So this is the volume of the dose by A plus B, and which is volume of the central compartment, and volume distribution in the post distribution phase. This one is larger because B beta volume distribution at the elimination phase takes into account tissue distribution too. So I will explain this thing a little later. So as you can imagine, we have more tissue volume than plasma volume. That's why this is bigger than that central compartment. So when we are calculating the dose, we have to consider always this one. So if we consider this, there will be a error in calculation of the dose. I will explain that to you later. Here this curve shows, again, if you take into consideration this two compartment, initially volume distribution is going to be much less with time. Is volume distribution, you see, volume of the distribution in the central compartment is goes up with time, and then it becomes the, so this is the volume of the central compartment. This is the volume of the central compartment, and this is the volume of the tissue compartment. It is always higher. So with time, the central compartment volume increases and it becomes this. This is the volume we should consider to calculate the volume distribution or dose. So if we use that wrong distribution, for example, you use this one, we have a curve like this. We know that this is a curve and then it goes like this. But now if we use this distribution, for example, this will be wrong distribution volume or wrong incorrect beta. If we have incorrect beta, that means everything will be incorrect. I will show you in the class that how those use of this is going to be incorrect. As you can imagine, again, here we have this curve and that curve. Now we decided to use in between, neither distribution nor elimination phase. So you will have a new beta for this, the slope. So if you use this slope, then you will have incorrect volume distribution, incorrect dose. I will explain this thing in the class. So now, possible question: how does plasma concentration decline in one compartment model? As you can see, plasma concentration decline like this. It's mono-exponential. And then how does plasma concentration change in two compartment model? Plasma concentration change in two compartment model like this. It is biphasic or biexponential. What is mono and biexponential decline? This is bi one. This is mono and bi. Here you have one slope or rate constant, and then it changes another rate constant. So this is biexponential. Do you have real compartment? If not, what are the compartments? We do not have real compartment. Compartments is just hypothetical, and we have two major compartments: plasma compartment, tissue compartment. When and why does one compartment will give erroneous data for drugs that exhibit two compartment kinetics? Here, as I have explained, we have this distribution pattern. If we use one of them in between, so it is always going to give us incorrect slope. In that case, it will be erroneous. The data will be which volume distribution is higher. As I have shown you, beta is higher than central compartment. Explain: collection of blood sample during the distribution phase will give erroneous data. Yes. Now I will explain this thing in the class. As you can imagine, we have a drug when it has two compartment kinetics, it exhibits two compartment, and the concentration is falling down like that. Now you collect sample during the distribution phase. When you collect sample during the distribution phase, it will, and the drug works in the central peripheral compartment, tissue compartment. You are collecting sample from here, then it will give you erroneous information. I will explain this thing again in the class. So it is long, but I hope this helps. and tomorrow I will explain everything in the class. Thank you very much.